question 5. So, for part A, several ways of approaching this. I've done this. First of all, I've just taken on board the fact if we're just looking at the forces going up and down, we can see the tension in A plus the tension in C together must equal the two weights, so must equal the 25G and the 60G. So nothing to do with moments, just forces going up must equal forces going down. So that gives me an equation involving the tension in A and the tension in C. So I've chosen to use that. Now here in red, I've taken moments about A. Okay, moments about A. So that takes TA out of play because obviously this string here is no distance away from A. So it will be some force times no distance, so that's 0. So looking at it from the point of view of taking moments about A, I've got this one and this one both going clockwise and this one going anti-clockwise. So I've got 25G times 2.5 added together to the 60G times 5 going clockwise and going anti-clockwise. I've got the tension in C multiplied by the distance of 4.5. So therefore my only unknown there is the tension in C, allowing me to work out the tension in C to being 790 newtons to 2 sig figs, and because up here I've said the two tensions together equal 85G, that allows me to work out the tension in A being the difference, being 44 newtons to 2 sig figs. Now equally I could have taken moments about C, which I've done up here in green, and that again would actually work out the tension in A to be my 44 newtons. So a number of ways of sorting out the two tensions. Now for part B, what we're saying here is we're saying it's still in equilibrium, so it's not moving, but we want to have the maximum weight we can have here. So think about it, we've increased the weight here to its maximum. It's not moving, but basically this string is all but going floppy. It's just about, there's no force here going upwards, so effectively our tension in A is 0, okay, as we make this weight as big as possible. So if we take moments about C, so really that's the pivot in the seesaw, okay, we've got our anti-clockwise moment being 25G times the distance of 2 from C, compared to our clockwise moment of a distance of 0.5 multiplied by an unknown mass going anti-clockwise times G. So that gives us that equation there, allowing us to work out the mass to be 100. So 100 kilograms. So for part 2, work out the greatest possible tension in the rope. Well, what I'm saying here is we've got so the greatest possible tension in the rope to the beam at C, as I was saying before, really all the tensions going through this string here, this one's effectively 0. So what have we got? What are our forces going downwards? We've got our 25G here being the weight of the rod in the center of the rod, and we've got our 100 that we've our force here of 100G going downwards. We've just worked out the mass to be 100 kilograms. Okay, so yes, I should probably put in kilograms here for the mass, 100 kilograms. So yes, so what we're saying is, so our two forces downwards are a 25G here and 100G here. So our tension going upwards is the two added together, 125G, which is 1,200 newtons to 2 sig figs.